what I would like to start with, yes, this entire course is going to be pattern matching algorithms. And I will, of course, say what does it mean, pattern matching algorithms. But I decided to actually start with what is the place of pattern matching in what we call computer science. So we'll start from outer space and we'll zoom in until we get to pattern matching. So we'll start. Computer science. It's a good thing that computer science is composed only of two words, because there actually are two problems with the name of our field. So we start with that. What are the two problems? Let's start with problem number one, the word science. Now, why the fact that it's computer science? Why do I say that the science is a problem? All right, we all know sciences. So let's see. All of these are sciences, and no problem about it. People will agree that they're sciences. Then there's also some things that most people will not think they're exactly sciences, and they're here on the other side. Now, all of you, when you look there, what jumps at you? And since you're not sleepless like me, it should jump at you. So the right side, which is sciences, is any of them called science? No, they have names. The biology, physics, chemistry, mathematics. These guys, political science, social science, creative science, behavioral science, some people would say they're soft sciences, some people would say they're not sciences at all. But the problem is, because of this problem, they feel like they need to jump up on a table and hit their breasts and say, I'm a science, I'm a science. So, being that that's the case, what group exactly do we want to be part of? So, our name being computer science is a problem. And that's problem number one. We'll get to that, but keep in mind, it's a problem. And we'll see why we have science in our name, even though I really believe it's a science. A number of years ago, when my young daughters were still in high school, and there was a Parents' Day, and so we went to the Parents' Day, and the computer science teacher said, well, okay, computer science is not a science. And she said that, and smoke came out of my ears because I was so angry. What do you mean it's not a science? But at least from looking at this, there's a point in what she's saying. So we're going to have to discuss that. And the second word that is a problem, in this case it's the first word, is computer. Now that's also a problem. So let's assume that computer science is a science. And indeed, there are now magnificent computers out there that are so fast and they can do so much. So yeah, it's wonderful. But basically, what does a computer do? A computer gets some input and it does an output, okay? So that's what a computer does in general. And in fact, other things do that also. So you take a washing machine, and there's also an input. You put in the dirty laundry, and it works, and then the output and the laundry comes out nice and sparkling and clean. So therefore, should we consider also maybe saying, well, we have washing machine science, and make a department and professors and teach and get degrees in washing machine science? Obviously not. Now, so you say, well, a washing machine is a simple thing. So you don't want to make a department out of a simple input-output machine like a washing machine. But the problem is that philosophically, to base a science on a machine is problematic. A science cannot be based on a machine because a machine is a very ephemeral thing. It's here today, it's gone tomorrow. Take another example. Okay, so this is a trireme. The triremes were the famous boats that the Roman Empire used, and with these boats they actually conquered the entire world. They were magnificent machines. So if the Romans in their university back 2,000 years ago had the trireme science department, and there's a science to it, exactly how to build it, and what about the hydraulics, and how does it go on the water, and how do we make it go fast, and how many times do we have to hit the slaves so that they row faster and don't die. I mean, there's a big science involved. Nevertheless, if they actually had a church-turing science department, that department would not have too many students today. It would not have too many students 100 years ago, and even 500 years ago, and even 700 years ago. Why? Because the church-turings aren't here anymore. They're a machine, and the machine was good for its time, and it's not good anymore because no one uses it. So it's not a science. It's a machine. So these are the two big problems about computer science. One, how is it that we even dare say that here we have a machine and we base it, and that machine, what it can do, gives us a science? That's a horrible thing to do. And the second thing is, why do we call ourselves a science? All right, so now comes the answer. These are the questions, now comes the answer. And I will start by saying that computer science is divided into three parts. Now, in Israel, whenever I say that something is divided into three parts, everybody cracks up and starts laughing because in Israel, everybody goes to the army. And in the army, they say that everything in the army is divided into three parts. So whenever I say that computer science is divided into three parts, Israelis laugh. Speaking about Israelis, yeah, we have to say a few things also. I taught Israelis and I taught Americans. I never taught Indians. So this is a good experience for me as well. Well, I had some Indian students in my classes in America, and by the way, they were better than the American students. And why am I saying better? Because, and that's what I'm going to urge you to do. What I like about Israeli students is they don't take anything for granted. If they don't understand something, they ask. And that's what I'm going to ask you to do. Today you're going to understand everything because I'm telling you stories and philosophies about computer science. Everybody understands philosophy. But soon we're going to get into science, and then there may be things that are not quite understood. So if you don't understand, ask. And the reason is that otherwise things build upon what you didn't understand, and then you're going to be lost for the entire duration of the class. So you don't want that happening. Another thing that I usually say to my students is that you're always not the only one who doesn't understand. If you don't understand, there are other people who don't understand. So don't feel embarrassed to ask, and don't feel, some people say, well, I feel stupid. No, because whenever someone asks a question, there are always going to be some people who are going to breathe a sigh of relief and say, I'm glad he asked because I also didn't understand. So you're doing a public favor if you don't understand something and you ask. And the third thing that I say to my students, now it is not so relevant here, but in general, when I give a course in the university, there's also an exam at the end of the course. So I say to the students, when you ask a question can't be stupid. If you say you don't understand something, a question can't be stupid. The answer can be stupid. So, but I'm the one who gives the answer. So someone doesn't understand, he asks the question, and I'm answering. So the answer can be stupid, but that's me, so don't worry about it. The question is not stupid, so don't feel bad. And I always tell my students that the same is true also for the exam. Questions are not stupid, only answers. But here, since there's no exam and I'm the one who is answering, feel free to ask. So, and the last thing is, I'm already glad to see that you're not Klingons. So also you can smile if something is funny. That's okay, because there are some people who believe that if it's a course and if it's a serious thing, then even if it's the funniest joke in the world, they have to stay like this. No. So if you think that something is funny, you can always laugh. And in my classes, I even say something else. If somehow when I'm talking, you can think of some joke or anecdote that is relevant, stop me and tell the joke, because we all want to hear it. So forgetting now about the jokes, as everything in the IDF, computer science is also divided into three parts. Now, the first part is obviously not computer science. It's not science, it's not even computers. The first part is gossip. And that's the main part of computer science. Most of what the world, when you say computer science, most of what the world thinks about is gossip. So, what company did what? And what did, how did C# compare? Why did the Microsoft come out with C# against Java? Or these are all kinds of gossips. This has always been the problem of computer science. That was the problem also when I was a student. And I was a student, don't ask, in the millennium ago. I mean, and still, there were only about 50 computers in the world, and IBM didn't think that the world needs more than 50 computers. But, and the computer that I worked on was a big IBM 360. When I was a student, that was the computer that the university had. It was amazing. It was magnificent. We had a hall about twice as big as this, and the computer was sitting there. And your cell phone is 100,000 times faster than that computer, and it has 30,000 times more memory than that big, huge hall that there was. But even then, most of computer science was gossip. So people were talking about gossip. And not only that, they also have no clue what computer science is about. People would ask me, so what do you do? And I would say, well, I'm a professor of computer science. And they would say, my daughter is also a key puncher in the discount bank. In those days, you know, they punched keys. So that's computer science, right? You sit there with the machine and you punch keys. And that's what I'm telling you, is a machine is not science. But the world thinks that everything is computer science. So computer science thinks we need to tell you, no, no, no. That's not computer science. That's like it has to do with computers, yes, but it's not a science. We are a science. And that's part of the reason why computer science felt the need to say we're a science, we're a science, we're a science. Because all along, from the beginning, everybody is part of computer science. Everybody. Everybody who touches a computer is a computer scientist. But that's gossip. Then comes the second part. The second part is already a serious part. That's the applications part. And I am not discounting this because it really makes the world go around. The applications part is amazing. And you who are young, you don't even realize how it has changed the world. But we know how it changed the world, right? Because, I came here today, passed through a number of airports, and I got a boarding pass in every airport. The last one was actually in Delhi. Now, in Delhi, I understand why I got the boarding pass, because they like to stamp it. So they stamped it with 5 different stamps. So they needed a boarding pass for stamping. But in general, if you don't want to stamp it, why do we need a boarding pass? What is the boarding pass? What does it mean? Why do we need it? And it's because of the days before computers. And I still remember my first flights. In fact, my first flight was out of India to Israel, and that one I don't remember. I was 3 months old. But flights that I already remember, when you go to a travel agent in the old days and you buy a ticket, can they give you the seat? No, because they're not connected to each other. So if you buy a ticket here in Gandhinagar, and they tell you, okay, now your seat is 13A. Someone else bought the ticket in Israel, and they tell him also it's 13A. At that point, there's a problem, because people always fight about these things. Nobody wants to stay behind. There was this guy in America that was dragged out of an airplane, and you saw what happened. So people fight about seats, so that can't be. So today it can be because everything is connected by computers. But then that wasn't the case. So what happened? You would buy a ticket. The ticket is for the flight. Then you come to the airport, and when you come to check in, there's a big picture of an airplane behind the counters, and they have stickers in all the seats. And then they show you, okay, the stickers that are already gone, these are taken seats. So what do you want? Okay, so I want those seats. So they take the stickers out, they put them on a card, and they gave you, and that's your boarding pass. So now you know where you sit. So that's an anachronism today, that you still have boarding passes. We don't need it. But this is how it was. You left one country to go to another country. In those days, there was something called traveler's checks. Nobody even knows what it is anymore nowadays. But that's what people did. You took traveler's checks because you don't want cash. Maybe you're going to be pickpocketed. Or, well, today everybody has a credit card. And why can we do that? Because there are computers. And there are computers everywhere. As I say, the world goes around. There are computers in the mixers. There are computers in the cars, in the brakes. Now, of course, they want the cars not to drive themselves. But even the cars that don't drive themselves, the computer drives the car. You don't really, when you really move the stick. So I have a Citroën. It's a French car. So it's automatic, but it also allows you to control the gears, because I feel that I do a better job changing gears than the program. So it allows you to change the gears by yourself. But first of all, you don't have to push a clutch. And secondly, you don't really change the gear. You just tell the computer, I want to go to gear 3. And it's done by the computer. So you're not connected directly. You push the brake. You're not pushing the brake. You're not connected to the rope that actually pulls the brake. It's all electronic. So the computers are everywhere, and it makes the world go around. But it's still not a science. So these applications are wonderful. They change the world. They're very important. It's not a science. So where is computer science? Okay, so the science in computer science is really theory. Now, it used to be when I was young, and I didn't mind picking a fight with all kinds of people, that I said, well, theory is only theoretical computer science. But then I became more mature, and then you don't pick fights anymore. So I say, well, it's not just theoretical computer science, but even the theory of computer science, which is really the science. So this whole thing is what the world calls computer science, which is why we feel like we need to yell science. But we are now coming to the science itself. And that is the small part of it. And that's divided into 3 parts again. And the first part is methodology. The methodology is the ideas of how do we actually automatically do processes in an automatic way, in a way that we can easily define, easily maintain, easily debug, easily explain. So all these things all the courses that you actually learn in computer science are all methodology, because we don't really teach you a programming language. Or we may do, but as an example. What we really are trying to teach you is the concept of programming languages, so that you know the difference between a functional language, an object-oriented language. What are the different concepts? What are the pros and cons of each one? Now here you're talking about a concept. You're not talking about a particular language. The languages the languages themselves, if you're looking at C++ or Java, or if you're looking at the old Pascal or Ada or any of these languages, so they could be examples of the concept that we're teaching. But the idea in programming languages are the concepts of programming languages. Operating systems. The first computers didn't have an operating system. You actually took control of the computer and you ran it. You did everything. You wrote the program. You had to deal with the interrupts that came in. You did everything. But then, what happens if a few people want to run on the same computer? What happens if you want to run a bunch of applications? So something needs to organize the situation. That's what the operating system does. And the operating system is an idea. That's the same idea. So the idea that I told you about a boarding pass, that idea is the semaphore idea. So that idea appears in operating systems as well. It appears there as not as an example, not as a but it appears as an idea. So the semaphore is an idea in operating systems, or queuing. So these are all ideas. And when we teach it to you, we want you to understand the idea, and we can give you examples to, sometimes it's easier to understand the concepts via examples. And it goes on and on and on. Information processing, database, software engineering, artificial intelligence, all the courses that we teach you a method of how to do automated stuff and to do it well. Now, what you see is that there's actually a migration, because if we're looking at programming languages, it's sitting here. You can learn about the different methodologies, but then there's going to be applications, because someone is going to come and sell you C++. And at that point, it's an application. It's not a methodology anymore. And then there's going to be the gossip, because people are going to say, well, you know, C++ is better than Java, or Java is better than C++, and people are going to tell you all these gossipy things. So everything moves from here to here. But although that's what most of the people do with computers, this is the science. All right. Then there's the next part of computer science. And this part is what can be computed. What can be computed is actually a question that is independent of a computer. Now we're getting to the question about how can we base a science on a machine. So what can be computed is really independent on a computer. Why? Because in fact, computability, which may be a course that you have, it's a course, or recursive function theory, usually in math departments. But computability is a course that many computer science departments offer. And the question is, what can be computed? Now, you're saying, well, what can be computed? What can be computed by this computer, by this Lenovo here? Or what can be computed by a Cray or an IBM 360? It would be a different question, because it's machine dependent. Well, it's not machine dependent. And this is the famous church-turing thesis. Did everyone hear about the church-turing thesis? So the point of the church-turing thesis is the following. So it turns out at the beginning of the 19th century, in the early days of the 19th century, that you had all these mathematicians dreaming up of computability models. So you had the Turing machine, which is a model, but it wasn't the only model. You had the Wang machines and the Markov algorithms, and of course the PRAM that we all know, the von Neumann machine. And then there's primitive recursive and recursive functions. So there's all these models of what different mathematicians said, this is what I call computable. And then what happens? Lo and behold, it turned out that all these models are equivalent. They're all equivalent. And they're really, in the 20s and 30s, that was the end thing to do. You come up with a computability model. If you're anybody who's anybody, you come up with your own model. And then they all turned out to be the same, which is amazing. Amazing. These things don't look at all the same. But they turned out to be the same. And by the way, this is something interesting also. I was once walking on the way to class to teach the advanced algorithms course. And I was going through, in my mind, it's an undergraduate third-year course in Bar Ilan. And I was running in my mind what I'm going to teach. And then I said to myself, this algorithm didn't even exist when I was a student. And then I said, wait a minute. Which algorithm in the course existed when I was a student? None. There is not a single algorithm in the entire advanced algorithms course that I teach that existed when I was a student. And I said, whoa, that's interesting. So then I started thinking about the other courses that we teach in computer science. And it turns out that somewhere in the middle of the second year, already everything that is taught wasn't around when I was a student. It had been invented afterwards. So I thought that that was amazing. But then I said to myself, so what did they teach us for 3 years? If today, in a year and a half, we teach what they taught me. But that's the kind of thing that they taught us. Because when I was a student, they actually taught us all these different models. And we actually proved the equivalence of the different models. So this is a really interesting question. What can be computed and what can be computed means what can be computed uh, by an automated form, in an automated form. Not by a machine, but in an automated form. Now, the church-turing thesis, after all these models turned out to be equivalent, comes and says, well, this is what can be computed. And nothing else can be computed other than what these models do. Now, it's a thesis and not a theorem because you can't prove it, but the idea is this. The mathematicians come and say the following. We are mathematicians. We're not bound by anything in the world. We have our wild imagination, and we're sitting there, and we're running amok with crazy ideas, and we all came up with this same set of functions that are computable. Then, Church and Turing say, then it obviously can't be that the physicists can build something that's more powerful than that. So that's why it's a thesis, but that's why it makes sense that it's a thesis. Because in a from a mathematical point of view, an organized, automated function is really a recursive function. And all these models. So that's what computability is. And that's, in some sense, the heart of what it is to be computable. And so when we say computer science, it is not computer science, it's computation. In fact, in Georgia Tech, where I was a professor for a number of years, they don't have a department of computer science. What they have is a college of computing. So they actually solved both of the problems that I raised. It's not science. The word science doesn't appear, not that it's not science. But the word science doesn't appear, and it's not computer, it's computing. So computing as a concept. So as a concept, we see that computability is a concept. And it's a concept that is independent of a machine because, in fact, when they started thinking about these models, there were no computers in the world. Okay, but then there's also the third part. And that is, what can be computed efficiently and how? Now, here we come again to a question that you say, all right, so what can be computed? We grant you, you're going to say, well, we grant you that what can be computed is a function, but what do you mean by efficiently? Why is that not dependent on how fast my machine runs? Well, it's not dependent on how fast the machine runs because, as you know, when we talk about efficiency, we talk about asymptotic efficiency. So the machine being twice as fast or 100 times as fast or 100,000 times as fast as today's computers are compared to the IBM 360 that I started work on. And the IBM 360 was a lot faster than the first computers that were actually built at the end of the Second World War. I worked with a guy in Dallas many years ago. I was 20 at the time. He was a serious programmer. He was 50. Now, when I was 20, he was 50, so you can imagine that he worked on the very first computers, on the computers when a bug was a bug. So when you say that you have a bug in your program, okay, so it's because it was a real bug. They used to have these vacuum tubes, and that was the computer, and a bug crawled into one of them, and the program didn't run. So he says, whoa, I have a bug in my program, and that's what the word bug in the program comes from. So he worked on computers when a bug was a bug. So he told me, when we parted company, he put his hand on my shoulder and he said, listen, you're young, you're starting a life in computer science as a programmer, so let me give you a piece of advice. Whenever you write a program, you're in a company, you're supposed to write a program, do two things. Put in a couple of loops, they're just empty loops. I mean, I goes from 1 to 100,000 or something. You put in these loops. Throw them in at random. And also define some buffers. In those days, the computer memory was 32K. So any buffer that you defined would take some memory from the computer, and that would be a problem. So he says you define some buffers that you don't use. Because, he said, at the lifetime of every project comes the moment when management says, okay, you have a month now, the system has to run 10% faster and with 10% less memory. You just take out your loops and your buffers and you go to the beach for a month. So that was the advice that John Sobieski told me. So it would seem then that when we're talking about efficiency, efficiency is dependent on a machine, but again, it's not. And as you know, it's independent on the machine because of all these courses that we're talking about, complexity. So when you're talking about complexity classes, NP, P, BPP, RP, all of these complexity classes, what are they? They're complexity classes of functions, not of machines. You don't define a complexity class on a Lenovo. You define a complexity class of functions. So even the complexity of a function, even the complexity is inherent in a function when we're talking about asymptotic complexity or polynomial complexity. It's not entirely true for linear time because, as you all know, a one-tape Turing machine cannot compute in linear time everything that a two-tape Turing machine can do. But when it comes to polynomial time, again, all these models are equivalent. So we have complexity. And then we have two other kinds of courses, data structures and algorithms. Now, data structures are the way that you organize your data in order to make things work. And algorithms is the process that you use in order to make things work more efficiently. Now, these three things, the difference between these two and complexity is the following. Complexity, I like to say, is studying a forest. So you have the forest of all functions. Complexity says, okay, let's look at the forest. We have pine trees, we have palm trees, we have all kinds of different trees. And so we study them by the groups of trees in the forest. These two are questions of a single tree. Here, I have a tree, and it's standing there right in front of me. How do I climb it? How do I get the fruit down? So how do I solve a problem? So these are methods for solving problems, and these are the study of different types of functions. But between data structures and algorithms, there's always, I don't know any algorithms people who don't deal with data structures. And in fact, we will see that in this mini course also, we're not, although it's supposed to be called pattern matching algorithms, but we're also going to look at data structures that do pattern matching well in various types of ways, not just algorithms. So there's no algorithms without data structures, obviously. Nevertheless, the difference is that a data structure really deals not with the process. It deals with how do I put the things together so that they'll work well. Whereas the algorithms deals with the process. So if you consider sorting, for example. So a heap is a data structure. So heap sort would be a sorting using this data structures, this particular data structure, the heap. Whereas if you're looking at bubble sort or insertion sort or even merge sort, there's no specific data structure that you're using. It's more the process that is doing the work. So that's the difference between data structures and algorithms. And this is where we are. So what we're going to be doing in the pattern matching in this mini course is going to be data structures and algorithms. So in the world of computer science, we are in this particular corner, but we're going to be dealing with a particular kind of problem, and that's the problem of pattern matching. But even more than that, it's the problem of search. So pattern matching Word is pattern matching because that's, again, like a boarding pass, boarding card. It started that way in the old days, but in fact, it's searching. And it became a lot more important now because there's so much digital data all over the place. And in fact, most of the digital data that exists in the world today, no one has ever looked at, and no one person can look at all the data. The physical data that comes from all kinds of the telescopes, the radio telescopes that are sitting there getting data from space. It's terabytes and terabytes and terabytes of data that no one can look at. So we are inundated with data. And so the question is, when you're inundated with data, you have to search for it. If you saw the movie Raiders of the Lost Ark, did any of you see that movie? Wow. It's a good movie, you can see it. It's an old movie, but it's good. It's an Indiana Jones movie by George Lucas and Steven Spielberg. They did it together. But the idea is it's this archaeologist who is looking for the lost ark of the temple, of the Jewish temple. The ark was lost back in the times of the Babylonians. They conquered Jerusalem, burnt the temple, and there is no trace of the ark since then. So in the Bible, there's stories about the ark. But after the destruction of the first temple in Jerusalem in about minus 500 BCE, 500 BCE, after that, there's no more trace of the ark. So the whole movie, the premise is that this archaeologist is looking for the ark. At the end, they find it, but the ark is so powerful that it kills people who don't deal with it well. And so they need to somehow hide it again. But even the first time when it was hidden, eventually it was found. So they're thinking, how can we hide it so that no one is going to find it? So they put it in a crate, and they put it in a big warehouse, in a big government warehouse in Washington. So you have there a huge warehouse with hundreds of thousands of crates. No one ever finds anything there. So it's going to be buried there forever. So that was the joke that the movie ends with. You want to lose something, just put it where no one can, with so much data that you can't reach it. So pattern matching, the whole idea with pattern matching is searching. So we want to efficiently be able to search for data in the huge amount of data that we have. So that's what pattern matching is about. Okay, so we finished with the first part. Any questions about where we are in the world before I now start about pattern matching? Everybody's cool. Okay. Now, since we are going to be doing a bit of science now, what I actually like to do is I have this PDF thing, and when necessary, I raise the screen and I write on the board. So that's what we're going to use. But so pattern matching. So as I said, we're inundated with data, and pattern matching is a big hammer, and that's a hammer that I hold in my hand, and I run around in the world and I see nails everywhere. So you bang and bang and bang because you have a big hammer. And today, again, because we have so much data everywhere, pattern matching really comes in handy from the following problem. And by the way, let me also say one more thing. There's a related field to pattern matching called information retrieval. It's related, but it's not the same. Information retrieval deals with retrieving words. And so it's something that people deal with who want to look at texts and retrieve from books and papers and that sort of thing. And it's easier than what pattern matching deals with, because pattern matching deals with heterogeneous data. So there's no assumption made on the particular data that we are retrieving or searching, like information retrieval, where the assumption is that you're retrieving sentences, words, paragraphs, whatever. Here, you say, well, maybe maybe what I'm searching for is a gene in the human genome. So you have a huge string of length 10 to the ninth, huge. You have this big string, and you're looking for a gene of length, let's say 3,000, and you're looking for that gene in that string. So where's the beginning? Where's the end? I mean, it's a stream. If you look for a piece of music, you have your notes, and you're looking for some particular piece of music. Again, what's the beginning and what's the end? You have your music, and you're looking for a particular piece. If you're looking for a picture, you're looking for some particular image in a big image. Where is the beginning? Where is the end of the image you're looking for? So, so as opposed to information retrieval, where you actually look for you look for words, in pattern matching, you look for things in data that maybe there's no beginning and end. I mean, you're looking for all kinds of things. And we're going to see all kinds of examples, because the various examples are going to show different algorithms and different techniques that have been developed to solve different problems. So so sometimes what I'm going to do is show you a problem and say, all right, now this problem was given, and therefore we now need to solve it. So what the original, the first problem in pattern matching, the most basic one, is the problem that Knuth, Morris, and Pratt dealt with. And it's the problem that I just said about the genome. So you have this big text, T1 through Tn. It's over some alphabet. When you're talking about a genome, n is equal to roughly 10 to the ninth, and the alphabet, each one of these elements is one of 4 bases. So it's an alphabet the size of 4. It could be that you're looking at something binary, and then the alphabet is going to be of size 2. And it could be that you're looking at an infinite alphabet. How can it be an infinite alphabet? Suppose what you have is a string of numbers. You measured. It's measurements. You measured all kinds of things. So you have numbers. It's infinite. I mean, you don't know what it is. The measurement up to the resolution, or there's an infinite number of numbers. And so at the moment, I am not saying anything about the size of the alphabet, although we are going to see that it plays a major and a critical role. But at the moment, I'm not saying anything. All I'm saying is we have a big text of length n, no beginnings and no ends. It's just a text, no words, no blank characters. And we have a pattern of length m over the same alphabet. Again, we're going to see cases where sometimes it's not necessarily the same alphabet. And what does it mean to find it when it's not the same alphabet? We're going to look at all that in the future. But right now, we're looking at the very basic pattern matching question. We have a big text of length n. We have a small pattern of length m over the same alphabet. So this would be your gene. This would be your genome. And we want to find all the occurrences of the pattern in the text. So we want to find all the indices I where the pattern starts. All right, so it's not such a hard question. It's not NP-hard. It's not Ackerman. I mean, it's not a hard question, because you can actually give this to first-year students, and they will be in a programming course. So, for example, you're going to be teaching programming next year, right? Or this year. Now, so this is an excellent problem that you can give already the first year. As soon as they know how to do loops and to work with arrays or something, you do the basic pattern matching problem. And there's no reason why they shouldn't be able to do it. Actually, years back when I taught programming, when I taught recursion, I was cruel, I don't know. But when I taught recursion, I gave them the definition of Ackerman's function. And I said, okay, program it. So there you go, they program. It's not really that hard once you know how to program recursion, so what's the big deal? But then they want to test it, so they test Ackerman 2020. And they work and work, they don't get any answers, they don't get any results. It was really funny to see. But, okay. At the end, I said to them, look, you have to test an Ackerman 3.3, something like that. You don't try 2020. All right, but pattern matching is not like that. You can actually take your text, and if the text is reasonable, if it's not 10 to the 9th, and most of the first year students are not going to run this on a 10 to the 9th text, they're going to run it on a text of length 500 or something, whatever. So it's not a problem. You take the pattern, and for every location I, you test whether that's where the pattern match. So you test, here, this is y. So you put the pattern here in location I, and you say, is P1 equal to Pi? If yes, is P2 equal to Pi plus 1? P3 equal to Pi plus 2? You check them all, and if all of them are equal, then you say, haha, in location I, the pattern match. Okay, and it's actually, this naive algorithm is actually very simple, and it can fit here in one blackboard. Where are we? Let's make it a bit smaller. So this is it. I goes from 1 to n minus m plus 1. Why n minus m plus 1? Because you're not going to go all the way to n. I mean, the pattern isn't going to match. Once it doesn't fit in the text, no reason to check for it. So I goes from 1 to n minus m plus 1. And let's start by assuming that it's a match. And then we're going to do this for loop and check every single one. And if any one of them is not equal, then we put match equals to 0. And at the end of this loop, if match is still equal to 1, then we output we have a match in location I. Otherwise, we're done. So very simple program. Can write it in year 1. And the time, and that's the crux, the time is O of nm. Because in the worst case, okay, you may say, well, you know, if you're going to get stuck, you don't really need to go all the way to m. But what happens if your text is A, and your pattern is A, B? So, or anything similar. I mean, for this particular case, you can try it. But you can write a special purpose. But you can always find something that is O of nm, even if you say, as soon as I get an error, I jump out of the loop. So O of nm is the worst case, and it's not a good worst case. Why isn't it a good worst case? Because if you take 10 to the 9th and you multiply it by 3,000, it's a big number. So 500 times 25, the computer isn't going to feel it even. So it's not even going to scratch it. 500 times 25, good. But 10 to the 9th times 3,000 could be the difference between running something a whole day and running it 5 seconds, if it's just 10 to the 9th, as opposed to 10 to the 9th times 3,000. So we don't like this O of nm. All right? We don't like it. So, but what can we do? So let's look at an example and see what happens, and if it gives us any ideas. Because once we understand the idea, we'll understand what Knuth, Morris, and Pratt did. So, if we look at the text, and suppose our text is what's written here, and suppose our pattern was A, B, C, D, E. So, the naive algorithm compared, it's equal, it's equal, it's equal, it's equal, it's not equal. And then it shifts and compares, then it shifts and compares. The question is, when you look at this, is there any reason to shift and compare and shift and compare and shift and compare? At this example, not in general, but in this example, if you're looking at it, what do you see? So all of these are equal. E is not equal to A. What can we deduce from this? That obviously there's not any reason in the world to check what happens here because it's not going to match. So you may as well, if the A is not equal to if E is not equal to A, you may as well shift the whole thing here to the A equals A and keep going. Because if this was A, this was B, this was C, this was D, then obviously any shift here is not going to match. Okay? Now, why is this observation important? It's important because if we never go back, if we just keep comparing when we advance on the text, then our time is going to be O of n, not O of nm. We get the m because we compare, then we go back and compare again to the same thing. Then we go back and compare again. But if we're going to do the comparison, and as soon as I get stuck, I'm going to go ahead and compare the next one here. And then if I get stuck, go ahead and compare the next one there. If that's what I'm going to do, then every element in the text only gets compared once, then my time is going to be O of n. And that's what I want. Okay. So it obviously does not make sense to try this because it's not going to match. And it doesn't make sense to try the next one because you see that it doesn't match. And it doesn't make sense to try the next one. Okay, but the problem with this example is you're going to say, well, this example is very unrealistic because all these numbers are different from each other. So obviously, it's not going to match. But let's look at another example where not all the numbers are different. So let's look at this example, this one. That's the text, that's the pattern. So we compare, 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 compare. D is not equal to A. So what is the next place that we want to try? How are we going to match this? Obviously, there is no reason to compare here and here because this is A, B, C. So A can't start here and A can't start here. So that obviously is not the case. However, the only place to try is to shift it all the way here. And then I know that the A is equal to A. And even then, I don't need to try anything because it already matches. Okay, so if I look at something like this, so if this is my text and this is my pattern, and if the D doesn't match the A, then the next place to try is this one. We're going to shift here. But if this is where we shifted, I don't need to try it because it matches. Otherwise, I wouldn't be able to shift. Because I say anywhere where I can't shift doesn't match. Anywhere where I can shift, it means it matches. So I also don't need to try. So any way you look at it, you don't need to go back and try. Either it doesn't match and then you don't need to try, or it matches and then you don't need to try because you know that it matches. So in this case, also we don't need to. We can just continue and see whether after this A we get a B, C, and D. And if we get stuck again, then we're going to move again. Suppose we had a B, C, A. So we'll move again, and we don't need to try, but we continue. We see whether after this B, C, A we have A, B, C, or A, B, D. Okay, so in this example, we also can go ahead and not go back. So what seems to be the rule? So far we looked at two examples. We saw one example where nothing matches. Then we saw another example where we said, okay, either it doesn't match and then I don't need to check, or it matches and then I also don't need to check. But what does it mean it matches? What's the rule? When do I say it matches and therefore I don't need to check? So the rule is the following. Because I'm tired, I'm not going to think too hard. I'll tell you what the rule is. Well, I guess you're not tired, so you can't think hard. But here's the rule. The rule is, if you compared the pattern, and you compared it all the way here, and it was not equal, what is the next place that you would want to check? So the idea is, look at the longest prefix that is also equal to the suffix, and that's what you can shift and continue from there. So that's the rule. The rule is find the longest prefix that's equal to a suffix up until now. You compare, everything is okay, everything is equal, and then you get an error. Find the longest prefix that's a suffix, and then you shift. Now, what you would want to do is not what's written here, really. What you would want to do is something else. Is this, does this go up manually or electronically? If it's electronic, it's a problem because it takes a long time, right? It goes very slowly. Yank, and then the whole thing would go flying up in O of 1 time. This is actually linear time. And let me tell you, in my university, it's quadratic time because it goes. So sometimes automation isn't for the good. In any event, what we would want to do is actually look for the longest prefix that's equal to this suffix. And if I know that that's the longest prefix that's equal to that suffix, it means that I can now shift, logically shift. I'm not really shifting anything, but I can assume that from here to here, everything is equal. And now the next comparison is going to be this symbol with the next symbol in the pattern. So that would be the best thing that we could think about. However, there's a problem with that, because that would mean that we really need to look at all the suffixes in the text and compare them to the pattern. And the idea of Knuth-Morris-Pratt was that I don't need to look at all the suffixes in the text. If I do my pre-processing just on the pattern rather than the text, then that's good enough. But if I want the pre-processing to be just on the pattern, then I cannot count this last element, and that's why the picture that you see here is the idea of Knuth-Morris-Pratt. So what they said is, take the pattern up to position K and figure out, in a pre-processing, you don't even have a text. All I gave you is a pattern. Figure out for position K, what's the longest prefix that's a suffix. Figure that out for every K. And if you do, you have this table. Now, that was the pre-processing. You built this table. Now you run through the text, and you compare one to another. As long as everything is okay, you continue. When you're stuck, you say, okay, now I have an error. I can't go on. But I can go to the table because I know that where do I have the error? I advanced K in the pattern. And I pre-computed that in the pattern, the longest prefix that's equal to the suffix of the pattern, the longest prefix that's equal to the suffix, I computed what it is. So now that I know that that's the one, I say good. So that's the next comparison that I need to do. And I'm actually going to compare this one again. I'm going to pay a little bit extra, compare it again, but continue from there. So I am not actually doing the entire, all the shifts, but I'm comparing this guy again. So that's the idea of Knuth-Morris-Pratt. They solved with this idea the problem of the fact that I don't want to look at the entire text because it's sufficient to look at the pattern. But they introduced a problem. They introduced a problem that they're going to need to now prove something about their complexity because they're not always going ahead. Sometimes they're going to compare the same text element twice, or maybe 3 times, or maybe more. So that is a problem that it's a challenge they're going to need to face. And we're going to see how they answer that. But in fact, what I just told you is the idea of the algorithm of Knuth-Morris and Pratt. That's the idea. The rest of it, we're going to see the implementation and the proof of complexity. But the idea is simple. Take your pattern, pre-process it, so that for every K, I know what's the longest prefix of the pattern that's also a suffix up until k, and put that down in the table. That's step number one. That's your pre-processing. Step number two is going to be your text scanning. And in the text scanning, what you're going to do is run on the pattern in the naive algorithm, compare, 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 except when you get stuck, you don't shift one, but you go to the table, and that tells you how much to shift, and you continue from the place where you were stuck. That's the KMP algorithm. Now we're going to see two things. Well, how they implemented it. Now I can bring it back down. Means goes up, down means goes down. I'll get used to Nook. And as I told you, the reason that we don't do this for every text is because we ignore the text and we build the table only on the pattern. And the reason it works, and that is something that you should remember even in the middle of the night if I wake you up and I say, why is Knuth Morris Pratt efficient? And the answer is because of the transitivity of the equivalence relation. And where did we use the transitivity? Let's go back to, here, we use the transitivity right here, because what we're saying is we have a prefix. We computed the prefix, the longest prefix that's equal to a suffix of the pattern. Now, if the pattern is equal to the text up to here, then the longest prefix of the pattern that's equal to the text is the same. Because if this is equal to this and this is equal to that, because of transitivity, this is equal to this. So transitivity is what makes KMP work. We're going to see, right after this, we're going to see another algorithm, the witness table algorithm. And it's also linear time. And again, because of transitivity. But where don't we have transitivity? Suppose your matching relation is such where there is no transitivity. We're going to see such matching relation. Take even the equality relation. Okay, so I'll give you an example right now. Take even the equality relation, but add a joker, a don't care character, a character that matches everything. So you have in the pattern A, B, C, like in the text, but you also have some things in the pattern that you don't care what they match. Whatever there is, you want to call it a match. At that point, there's no transitivity anymore, because a don't care in the pattern may match an A in the pattern. A don't care in the pattern may match a B in the text, but A is not equal to B. So you don't have the transitivity, and it's not going to work, which is why once you introduce a don't care character, you don't have, there is no known linear time algorithm for matching. And we're going to need other kinds of tools and techniques. So here, because of the transitivity of the equality, we can use it, and that's what makes the whole thing work. There's even a picture here. See, because I didn't sleep at night, I forgot. So here's the text. We matched the pattern. Everything was equal up to here. In our table, this is the longest prefix that's equal to the suffix. But this text up to here matched the pattern. So this suffix is equal to this suffix. And therefore, the longest prefix that's equal to the suffix of the text is the same as what was pre-computed for the pattern. Now, so Knuth, Morris, and Pratt actually said, let's do this in a smart way. Let's write this as an automaton. Let's not build a table, but let's build an automaton. Now, in fact, that's in those days, it was the natural thing to do, to build an automaton, because automata theory, this is we're talking about 1972, this algorithm. So in the 70s, automata theory was the height of fashion. So you had the Greibach normal form and the Chomsky normal form and all of these things. Everybody was talking automata. So thinking about automata was actually quite natural at the time. But in fact, the automaton thing works, because why shouldn't it work? I mean, what does an automaton do? You build an automaton to decide something, right? So you go forward in an automaton, and if something doesn't match, you go back, and you go forward, and you go back until you find what you find. So it's a very natural thing to do. So what they're going to do is build an automaton that basically a success arrow is going to be when I match. That's when the pattern matches the text. And a failure arrow means it didn't match, but then let's go back to the shift of the longest prefix that's a suffix. So we go back to, in the automaton, to the next letter that I want to compare. And at that point, it's really easy. You go forward, and then you go with the failure function, and then you continue with your automaton. So let's look at an example. Nothing like examples. So they take the pattern P1 through PM, and they build an automaton. So that's the starting state, and that's the accepting state, M. And you have states from 0 to M. So you start your automaton, you put your finger on the text, and you say, is P1 equal to what I'm pointing to? And if it is, you go to state 1 and you continue on the text. Then you compare it to B2, and if it's equal, you go to state 2 and you continue in the text, and so on. You continue in the text until you get to the end. And if your pattern was there, you found it. So these are called the success arrows, the success links. So whenever there is a pattern, you start here, you compare, 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 everything is good, and you get to the end. In a real automaton, there actually are going to be a bunch of back arrows, right? Depending on, suppose the next thing that I'm looking for is not equal to P3. So what was it? If it was A, I go here. If it was B, I go there. I mean, that's what we would do. And that's what they didn't want to do, because that would make the time too long, surprisingly enough. Because even though the number of comparisons on the text are going to be linear, but what are you going to do in an infinite alphabet when you have a bunch of back arrows? Then your time is already not linear to even find what arrow to follow. So you need to do some sort of a binary search, and you're going to get a logarithmic slowdown. And so it's not going to work. And they wanted something that is independent on the alphabet size. There is no log of the alphabet size. So if you have all these alphabet symbols going back in a real automaton, you're going to get log of the alphabet size, and they wanted not to have it. So that's why they have two arrows. They have a success arrow, and they have a fail arrow. And fail means I didn't find P3. So that's the failure link. And where a failure link points, so a failure link from node I points to node J, where J is the length of the longest proper prefix of P that is also a suffix of P ending at PI. That's the picture that I drew for you. That longest prefix that's equal to the suffix. So the back link is going to point exactly to that. So we're going to now do this example. Okay, so suppose that our pattern is ABA, BA, BC. So this is the Knuth, Morrison, Pratt automaton right in front of your eyes. You're going to have 7 states, because 1, 2, 3, 4, 5, 6, 7. So you're 8 states actually, from 0 to 7. And the symbols that you're looking for in every success arrow are exactly the symbols that are in the pattern. So those are the success links. Now, in state 0, there's another success link. And that's this one. Anything that's not an A is a success link, but it points to state 0. Now, why do I call it a success link? It's not an A. But it's a success link in the sense that I move on. A success link actually means that I move on in the text. So every success link, if the text is equal to A, I move on to the next element in the text and I move on in the automaton. It's equal to B, I move on. Now, if I am starting the text until I find an A, every not A, I'm going to continue running on the text. So it's really a success, even if I don't find an A. So it's a success link, but it doesn't have an infinite number of things I need to check because I only check for A. If it's A, I move on, and I move on to on the text and I go to state 1. And if it's not A, I move on the text and I stay in state 0. But in every case, I move forward in the text. And that's why it's called the success link. So all the blue links in this picture are all success links. The black links are failed. And as you notice, I don't, unlike here in the success links where there actually are symbols from the alphabet, and in every automaton, failed links would also have symbols from the alphabet, but here we don't have symbols from the alphabet. We just write fail. And what does fail mean? It means that you compared, you didn't find. So you had A, B, A. You were looking for a B, but you didn't really find the B. There was something else that was written there. So what does it mean? It means that you need to find the longest prefix that's equal to the suffix here, shift it according to that, and compare again. Don't move on the text, but shift and compare again to where you are in the text. So I had A, B, A. I didn't see a B in the text. So I don't move on the text. I go in the failure link. Where is it going to go? What's the longest prefix that's equal to a proper prefix that's equal to a suffix in A, B, A? Which one is the longest? A. A, B, A. A is a prefix that's also a suffix. A, B is already not a suffix because it doesn't end with A, B. It ends with B, A. So the longest proper prefix that's a suffix is A, which means that in essence, what you want to do is stay in this letter in the text and shift the pattern so that you looked at A and now you want to compare the next letter in the text to the letter following that A. But if you're looking at automata, that's exactly what it means. You didn't see a B, so you're going to shift here. That's the longest prefix that's equal to a suffix. And what does it mean? It means that I already found an A, so I'm here, and the next symbol that I'm looking for is this one. Now, this example shows you the problem that KMP are going to need to deal with the complexity. Because in order to gain the fact that they only have one back arrow, now they're going to, why did I look for the longest prefix that's equal to a suffix? Because I had a B. Sorry, because the text did not have a B. But if you go back here, what are you going to ask the text? Do you have a B? I know already that I don't have a B. So we're going to fail again. So we're going to go back here, ask if it's a B, fail again, and then we're going to go here. Because that's the failure link now. Anything that's of length 1, the proper prefix is null, the longest proper prefix. So we're going to go here. And at this point, if whatever wasn't a B was an A, then that's good. We're going to go forward. And if it was something else, then that's also good because we're going to go forward because now we're already in success links. But what you see here is the big failure, or the big challenge of KMP is the fact that I don't just follow the failure link once, but I may follow it more than once. I followed it here, and then I'm going to follow it again because the B is not equal. If it wasn't equal to B the first time, it's not going to be equal to B the second time either. So I'm going to follow it again. The way to solve it would have been if we actually asked what was here, and if it was something that had a prefix, we would go to the appropriate prefix and not go back until we get there. So we go straight there. But that would mean that depending on the letter on the text, I'm going to need back arrows, which we don't want to do. So this is how they build the automaton. Let's take another example and see how these failure links work. Suppose I saw A, B, A, B, A, and then I didn't find the B. So we need the longest prefix that's equal to a suffix. So A, B, A, B, A. What's the longest one? A, B, A, right? So from here, we go here, because ABA is the longest one. So that's the next comparison that we're going to do. So in short, Knuth, Morris, and Pratt build this automaton. They have the success links. They have the failure links. Every failure link points to the longest prefix that is equal to a suffix up until the failure. Another question is, how can you do that fast? Well, we're going to see how to do that fast, but let's also point out something else. Suppose even you don't know how to do it fast, but your pattern is small. Your pattern is 3,000. Even if you work on it quadratic time, you're still going to work 10 to the 6th and not 10 to the 9th. So you're still going to work less than n, and your time is going to be O of n plus something less than n. It's still O of n. So in reality, the patterns are generally smaller than the text, and generally significantly smaller. At that point, even if I need to actually pre-process the pattern and pay more, but it's worthwhile, rather than multiplying the length of the pattern by the length of the text. So I still gain. Nevertheless, I will again tell you that we're going to see that they can do that in linear time. They can build this automaton in linear time. Yes. I see that there's even an example here. So let's an example run. So I'm going to make this whole thing smaller and run the example. It all fits on the board. So let's run it and see what happens. Maybe I can make it even smaller and then write on the board. You can still see it? The text and the pattern, everybody can see it? You have strong young eyes? All right, now I push the down button. Now, I actually wanted to make it small because I want to write on it. Excellent. Okay. So this is our text, and this is our pattern. As we said, this is the automaton, and this is the text. So let's start running. We have an A, and we're starting the text. We're starting the automaton. So we have an A, and that is an A. Okay. So we move on to this state, and in the text we move forward because it's a success arrow. Now we find the B. So we move on to this state, and we move the text. Now we have an A again. So we move here, and we're in state 3. And we have a B again. So we move here. All of this is very good. Now we're in state 4, and we want to see an A in the text. That's what the automaton wants to look. But what it sees is a C. And so it says, ooh, that's bad. So what do? We follow the failure link. Failure link goes here. What does it mean again? look at what it means as far as what we explained. We had AB, AB. So we want the longest prefix that's a suffix, it's AB. So what we actually did was we moved the pattern here, AB, and now we want to compare the C to the next element here. But all that happened just by following the failure link, because we followed here, which means the AB was already looked at, and what we want to see is that the next element fits. But the next element here is A, and here we see a C. So that's still not good. So we follow the failure link again, and we go back to the 0. So we're still here in the text. We followed 2 failure links. We're now in the beginning. At this point, that's a success link, because that's a C. So we stay in 0, we move on. We see a C again, so we stay in 0, we move on. We see an A. Good. So we go to state 1, and we move up to here. We want to see a B, and we don't, because there's an A in the text. So we follow the failure link, and we compare, and that's an A. So we move here, and we get a B. Then we see a B, so we have an A. We see an A and a B. And then we move here, and there's an A. So we move here, and there's a B. And now what we want to see is a C, but there's an A in the text. So we follow the failure link. What does the failure link mean? Again, where are we? We saw A, B, A, B, A, B. The longest prefix that's also a suffix is A, B, A, B. Right? A, B, A, B, and it ends with A, B, A, B. So the failure link goes here. So that's A, B, A, B. And this is where we are. So we see an A, and we continue. We see a B, and we continue. We see a C, and we say success. And indeed, that's the only occurrence of the pattern, A, B, A, B, A, B, A, B, C. A, B, A, B. No, it starts here, right? A, B, A, B, A, B, C. So that's the only occurrence of the pattern. So we found it. That's the algorithm. We understand why they did what they did, but we now see all these failure links that we continue going again and again, and we're a little uneasy about that. Because the whole idea is that you want to count the number of times that you compare every element in the text to an element in the pattern. And if you're going to follow all these failure links, like we did from here, in fact, that we had this example. We followed here and here and here. Well, we could follow all the way back. I mean, suppose here there wasn't a C but a D, right? So we would go all the way here. And that's O of M. So we could work O of M and that single element in the text. So that's disturbing. So we need to see what we can say about that. Okay, let's make it big again. So what we're going to do now is actually count the time that this algorithm worked. And the way to count the time that the algorithm works is actually natural. Let's see how many success links we followed and how many failure links we followed. So take a run of the automaton on the text. If you add the number of success links that you followed and the number of fail links that you followed, add them both together, that's the total running time of the algorithm. So it's not just the number of times that we... All right, so it would be easy if we always move on when we make a comparison on the text, but that's not what happens. We sometimes stay on the text a long time, and therefore that's not how we can count the running time. So the running time is going to be like this. Let's count the success links and the failure links. The number of success links is clearly O of n, because in a success link we saw, those were the blue ones, every success link we move forward on the text. So you cannot move forward more than O of n times. Once you move O of n times forward, you're out. You fall at the end of the earth. There's what? There's like 3 elephants holding the earth, and you fall at the end. So they're on a turtle. And so you can't go past n. But the failure links are a big headache, because it could be up to m in a row until the start node is reached. And then we only have the forward link. So if the failure links are going to be at every time O of m, then we got our O of nm. O of nm, back to the drawing board. That's not, that we did already in year 1 when Professor Mishra gave them the assignment. So we didn't need Knuth, Morris, and Pratt for that. However, the key point here is that that is not exactly true. You cannot really have a failure link every time. So you can't have O of n times m, because you can't do m failure links at every location. Why not? Because what does it mean, a failure link? A failure link means you go back and back and back and back. Once you went back m times, you're in the beginning of the automaton. In the next step, you can't go back m times, because you're in the beginning. So you only have a success link. So we see that there's something amortized going on here, and we're hoping that it's not really going to be O of nm, because to go back, you needed to go forward. So, but we need to count this. So like every amortized thing, we need to prove that actually, even if crazy things happen, you go a little bit forward, a little bit back, a little bit forward, a little bit back, you can't really get to anything quadratic, or not quadratic, O of nm here. So that's what we want to prove. So we're going to do it in a formal way. And this is one of the easiest ways of formalizing amortized analysis. That's by using a counter. So let's define a counter f, and we initialize it to 0. And this counter is going to do the following. You increment the counter by 1 when you follow a success link. And you decrement the counter by 1 when you follow a failure link. So that's what's going to happen. We have this counter. Now, this is not so far-fetched, because, let me tell you, back in 1976, at that time, I wasn't doing algorithms. I was, in fact, in officers' school. And if you think about 1976, that was also when the Entebbe raid happened, when an airplane was hijacked to Uganda, and the hijackers said that they want a whole host of terrorists freed unless Israel does that, they're going to kill the hostages. And Israel sent a team of the General Headquarters scouting unit all the way to Uganda, and they rescued all the hostages and flew back to Israel. That was called the Entebbe raid. There are movies about that also. That happened in 1976. And the commander of the Entebbe raid was called Yoni Netanyahu. He was the brother of the current president, of the current prime minister of Israel, Bibi Netanyahu. So his brother Yoni was the commander of the General Headquarters scouting unit, and he was one of the only casualties in that entire operation. There were very few casualties, but he happened to be one who was the commander of the raid itself. But his second in command was called Matan Vilnai, and he was and he came back to Israel, and he was the commander of officer school when I went through officers training. So we all obviously idolized him. But he came one day when we were in a shooting range, and he saw, to his dismay, that not all the bullets in the range hit the targets. And so he got so angry, and he said, "That's it. this can't go on. The army gives you bullets in order to hit, not in order to miss. So therefore, every bullet that you miss, you're going to pay the cost of the bullet. Now, let me tell you, it did wonders to increase the efficiency. Everybody all of a sudden started hitting because nobody wanted to pay. So, but the idea is the same thing. If you shoot a success arrow, I mean, this is even more liberal than Matan Vilnai. He says, I'm going to pay you if you succeed. So I'm giving you a, how many rupees is $1 nowadays? 65? So I'm going to give you 65 rupees for every success arrow, but if you fail, you're going to have to pay 65. So it's $1. So this is what we're going to do here. Now we're going to prove the following claim. At any point during the run of the algorithm, if the automaton at this point is in node K, then the counter has to be greater than or equal to K. Okay, so we're going to prove this, but again, think of what it's saying. I'm giving you a $1 for every success link and taking back $1 for every fail link, but I'm still, no matter how many successes and fails and whatever happens, I'm still going to say that any time that I freeze the algorithm and I say, okay, the automaton, what state are you in? And you say, I'm in state K. I'm going to say, well, then for sure you have in the bank more than K dollars, or no less than K dollars. So that's what we're going to prove. And we're going to prove this by induction on the number of moves I of the algorithms, Now, induction is a wonderful thing, and we're going to prove it by induction. Did you ever hear the proof that all horses have the same color? Proof by induction? No? Okay, so here, I'll prove to you by induction that all horses have the same color. Okay, let's look at a set of one horse. All the horses in the set, I mean, that's the base case of the induction, one horse. So obviously, all the horses in that set have the same color. It's one horse. All right, good. Now, assume that no matter what K I take, you have K horses. They all have the same color. Now, take a set of K plus 1 horses. All right, let's take one horse out. Now we only have K horses left. So obviously, they're the same color. Good. So now, I put that horse that was outside in, and I take one horse out, and I still have K, so they're all the same color. Now, they all used to be the same color as the horse who's out. Now, so therefore, all of them have the same color. Here's a proof by induction. The problem is that you're going to tell me that you can bring me counterexamples. So there's something wrong with this proof by induction. What's wrong? The base case is good, and for K is equal to 2, it's good. But for K greater than 2, it's good. But for K is equal to 2, that proof doesn't work. So induction, you have to be careful, but so that you can't prove that all the horses have the same color. Because if you have 2 horses, you don't have this transitivity property that we spoke about. So you take one horse out, whatever is left has the same color, good. Now you take it out, you put the other one in. He has the same color, but the one that's out and the one that's in don't have the same color. If you had 3 horses, then that would be true already. But since the induction doesn't work for 2, even if it works for 1, it fails. But here, it's going to work. So the base case is I equals 0, which actually brings me to a famous joke that if you don't know it in India, you should, and if you do, stop me. So they ask a mathematician to prove that all numbers are prime. So he says, okay, 1 is prime, 2 is prime, 3 is prime, so by induction all numbers are prime. All right. So then they ask a physicist to prove that all numbers are prime. So he says, okay, let's see, 1 divides only by itself and 1, good. 2 divides only by itself and 1, so it's prime. 3 divides only by itself and 1, so it's prime. 4, measurement error. 5 divides only by itself and 1, so it's prime. By induction, all numbers are prime. So then they ask an economist to prove by induction to prove that all numbers are prime. So he says, okay, 1 is prime, 2 is prime, 3 is prime, 4 is prime, 5 is prime, 6 is prime. By induction, all numbers are prime. Economist. Then they ask a computer scientist to prove that all numbers are prime. So he says, 1 is prime, 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 1 is... All right. So now here, our base case, now that we understand induction from all directions, our base case is I equals 0. What does it mean I equals 0? That we didn't do anything yet in the algorithm. We're in move 0 of the algorithm. So we didn't do anything. It means we are in state 0, f is equal to 0, we didn't do anything, f is greater than or equal to 0. So the base case is obviously true. Now the induction hypothesis says that after move I, if the automaton is in node k, then f has to be greater than or equal to k. Now we need to prove that after move I plus 1, if the automaton happens to be in state k, then f is greater than or equal to k. So let's see what are the cases. And there are actually only 2 cases that are possible. Case number 1 is that we used to be in state k minus 1. We had a success link, and now we're in state k, and that was move I plus 1. Okay? So move I plus 1, we're in state k, and we got here because we followed the success link. Now, the induction hypothesis says that f was greater than or equal to k minus 1 before we moved on this success link. Success link, what does it mean? That you get your dollar, right? So now f got 1 more, so f is equal to old f plus 1. You bump f by 1. And it's true that also k minus 1 got bumped by 1, but since f was greater than k minus 1, the new f is greater than or equal to k because both of them just got bumped. So if you follow a success link, clearly the induction hypothesis holds. The question is, what happens if you follow a failure link? Okay, so the failure link means that the move I plus 1 was a fail. So after I failed, I got here to k. And I actually pay, so I'm losing. So I was here in this state, j, and I knew by the induction hypothesis that f is greater than or equal to j. But now I have this failure link, and I got to k, which means that I subtracted 1 from f because I missed. So if you miss, you pay. So I subtracted 1 from f. However, since this is a failure link, it means we subtracted at least 1, probably even subtracted more. So although f is smaller, but he's smaller by 1. K is smaller by at least 1. So f is still greater than or equal to k. So that proves our claim. So f is always greater than or equal to k, no matter where you are. It starts greater than or equal, and then if you have a success, we saw that it's okay, and then if you have failure, even though you deduct, but you also go back. So it's always the case that that f is greater than or equal to k. Now comes an interesting thing. So here we have to be an economist. Suppose that your annual salary is $10,000. You're a computer scientist, $100,000. So suppose your annual salary is $100,000. Now, I tell you, I don't know how you manage your business and how much money you spend every month or every day. I have no idea. But what I do know is that you never got into the red. You always had at least $0 in your bank account in the entire year. If I give you these two facts, how much money did you spend throughout the year? Could you have spent more than $100,000? No, because if you did, you would have been at a deficit at some point. And I told you that you weren't at a deficit for the entire year. So even though I have no idea how you spent your money, but if you weren't at a deficit, it means you didn't spend more than $100,000. That is the story. Now, what is the meaning of the story? Well, F is our salary. And throughout the run of the algorithm, because we said already that we follow exactly n success links. So F, from beginning to the end, your income during the year was n. And you were never at a deficit, because F is always greater than or equal to K. And K goes from 0 to M. So you were never, F was n, you were never at a deficit. It means, how many failure arrows did you follow at worst? N. You couldn't have followed more than n failure arrows, because if you did, F would have been less than 0. And we proved that it never is. And F is exactly n throughout the run of the algorithm. That's your annual salary. So the conclusion from this is that since F is incremented at most n times, and it's always non-negative, then it's decremented, that's the fail links, at most n times. So what's the conclusion? So the total time text scan for the Knuth-Morris-Pratt algorithm is O of n. Because although sometimes we follow a whole host of failure links, but altogether we never followed, through the run of the algorithm, we couldn't have followed more than n of them. So we have n success links, n failure links. Your time is O of 2n, which is O of n. So the KMP algorithm is linear time. And it's linear time. Now here we're going to look at something else. It's linear time no matter what the size of the alphabet is. Because what do we care what the alphabet size is? All we care about is whether we follow a success link or a fail link. So even in an infinite alphabet, even if your alphabet was numbers and it's infinite, you're still going to spend O of n time on that alphabet, on that algorithm. Okay. So now we're almost done. We're almost totally happy with KMP. And the question is, how do we construct the fail links? Because remember, we said we don't mind if it takes us a lot of time to construct the automaton, but you do that when you don't know how to construct it fast. If you know how to construct the automaton in linear time, then you don't say, okay, fine. Then you say, I can do it in linear time. So we can do it in linear time. And this is the idea. The method that is done is exactly the same method as the search. In other words, you construct the automaton from left to right. Now, we know how to construct it for the success links, because that's just, you put them all there. But now we have to put the fail links in. The fail link of this one always goes back to the beginning. So we know how to start. This is the first fail link. And then we need to go on. So here comes the inductive step. The inductive step says, suppose that I constructed the automaton all the way up to here, and the fail link, I'm excited about the fact that this goes up in linear time and not quadratic time. So we have this fail link that goes up to here, and in fact we constructed all the fail links all the way up to here. But then we got to K, and K has some success, but we have to figure out where does this fail link go. So that's the question. We have all the fail links up to here, where does it go? Okay, so again, let's look at an easy case. let's look at this fail link, the k-1 fail link. And suppose it went here to I. And let's assume that A is equal to B. That this A is equal to this B. Then where is the fail link of K going to go? It's going to go to I plus 1. Does everyone see why? If anyone doesn't see, tell me, and then some other people are going to be happy. Fine, I'll tell myself. All right, you make it difficult. I always tell also my classes, every once in a while I like to do votes. I say, who thinks that this is like this and who thinks that this is like that? And what happens is, you would think that it's a binary question. Who thinks A, who thinks not A? So you would have half the class here and half the class there. So it doesn't happen like that. I say, who thinks A? And then 3 people raise their hands. And who thinks not A? And then 5 people raise their hands. And 50 people don't think. Not A and not A. All right, so why is that the case? Because remember, what does the fail link mean? It means that this is the longest prefix that's equal to the suffix up to here. That's what the failure link means. Now, if the next symbol, A, is equal to B, it means that I can extend this by A and this by A because they're equal. And then this has got to be the longest prefix that's equal to the suffix. There can't be anything longer, because if there was, then you would have a longer prefix that's equal to a suffix before. Since this was the longest prefix that's equal to the suffix here, then if you add A, which is what we did here, then the longest prefix that's equal to the suffix is just going to be with the added A. So therefore, if A is equal to B, that is the failure link. And that we did in time O of 1. But what happens if A is not equal to B? Well, if A is not equal to B, then obviously this is not the longest prefix that's equal to the suffix here. So we'll follow the next failure link and ask if this is equal to B. And if it is, then the failure link is going to go here. And if it's not, we follow the failure link again until the beginning. So what you see here is a construction that's amazingly similar to the run of the text. And so we have the gut feeling that it's linear time. And in fact, it is. So what we're going to do now is the following. I'm not going to prove to you, because I want you to have something fun to do tonight when you go home. So go home and prove to yourself how you can use a counter. What counter are you going to use in order to actually show that this construction is time O of m. So it's a cute little exercise, and whoever doesn't want to do it isn't going to do it, and whoever wants to do it is going to have tremendous amount of fun. So I highly recommend it. And has any of you read the book about Nash? A Beautiful Mind. So there was also a movie. The movie wasn't as good. The book was really good. But in the book, there's a story there about the Institute of Mathematical Science at Princeton, because Nash was in that institute. And at that time, the institute at Princeton was great, because von Neumann was there and Einstein was there. I mean, the Institute of Mathematical Sciences at Princeton at that particular time was an awesome place to be. And they also had awesome graduate students. But both the professors and the graduate students, being mathematicians, were a bit dizzy. And their minds were in all kind of in the stratosphere. They didn't exactly see where they were walking. And so in the book, there's a story about, he actually even gives the names. But some professor was teaching something to the graduate students. And And he told them about something that it's an open problem. But one of those grad students thought that what he meant is that that's homework assignment. And so he went home and solved it. And the next day he came back, and it was right. And it was, I mean, it was the solution to an open problem. So I tried to do that also, but I never got any serious solution to any open problem. Here, this is not an open problem, so you don't need to feel too bad. But as far as mathematicians go, there's also a story that a friend of mine told me about some famous mathematician that came to University of Chicago for a short time sabbatical. So he used to live in a neighborhood south of the University of Chicago. But immediately to the south of University of Chicago is a very dangerous neighborhood, not very safe. And then he lived below that, which was a nice neighborhood. So in the daytime, he would walk to the university, but at night, he was told, you don't walk home. At night, take a cab, don't walk at night. Okay. But one day, he was working and working and working and working and thinking and theorem and proving, and it got dark, and there was nobody left anymore in the building, and he saw that he forgot his wallet. He didn't have any money. So he says, what can he do? He has to get home. So he made himself as brave as he could, and he starts walking. And it's a shady place, and he goes into some alley, and half of the lights are broken, and his heart is hammering. And then there's this big, dangerous fellow walking towards him, and he's trying to like make himself small and pass by the side. And this guy brushes by him. And then he comes home and he tells his wife the story. And he says, and then as he brushed past me, I realized that he managed to take my watch. So I yelled at him and said, give me that watch right now. And you know what? He gave it to me. So his wife says, but dear, you forgot your watch at home today. So, so that's as far as mathematicians are concerned. So, all right. So so once we add that exercise, what we get when we put the two of them together is that we managed in time O of n plus m. M is going to be the pre-processing, n is going to be the running, but m is smaller than n. So really, linear time, infinite alphabets, we can do the matching. And that's the KMP algorithm.